Hello everyone, this video is about antenna array. Antenna arrays is basically a set of multiple connected antennas which operates as a single antennas. And I got it wrong here. So let's take an example. In this uh, antenna array is lying up along the z-axis, the z. The antennas on its own will radiate a beam, and that's why I said the end result is expected to be a steerable beam. Steerable means that the direction of the beam can be changed. So this is what the antenna array is about. And with an individual antenna, you may not be able to do this. For instance, if we have an antenna and we may be able to end up with a beam, yeah, if you are careful enough. But the beam's direction is fixed. But with an antenna array, you will be able to change the direction. So that's the beauty of these technologies. And before going forward, let's take a look at an ordinary antenna array. And in an ordinary antenna array, the spacing between two labeling elements are usually fixed. Just like in this example, the spacing between the first and second element is d, and uh, between two labeling elements is d everywhere along the antenna array. Suppose uh, the antenna array here is to radiate a beam, and in a far destination, we have a receiver here. It is very, very far. And in this case, because of the distance between the antenna array and the receiver is very long, very far. And uh, the direction of each antenna array will not be very much difference. And if you just zoom in the antenna array, most likely with respect to these destinations, you will see the radiation uh, the radiation from each individual antenna would be the same. The direction would be the same. And most likely, they would appear parallel to you. So if the angle here is theta, then you will also encounter theta for the second antenna. And for the rest of the antennas along the antenna array, the angle, the direction with respect to this receiver will be the same because of the distance. The receiver may be somewhere here, very, very far. It's not as not that close, very, very far. So if the distance is far enough, then you from the microscopic point of view, you may end up with something in parallel. The radiation is running in parallel. And in this case, this one is pointing to the receiver, and this one is pointing to the receiver in almost the same direction. And uh, this one the same. So the radiations from the first one and from the second ones are the same in terms of direction, but they are not the same um, in terms of the delay. So this one may arrive at the destination first, but this one will be later. And how late? It depends on the phase difference. So in this case, the phase difference can be calculated according to the right angle triangle here. And starting from this point, then the distance between here and the receiver will be exactly the same as between this point and the receiver. Uh, so the difference here will determine the delay. And how much is this little distance? This is path difference, so-called. The path difference, according to the diagram here, is d cosine theta. And this d cosine theta is a path difference between these two elements and between all other neighboring elements. Say in this case, this one, we also end up with a path difference here. And obviously, the second one and the third one will also have a path difference, d cosine theta. And now, to translate this distance into a delay, we need to find a phase. The phase, the phase difference, the path difference between two neighboring elements. Maybe in this case, is equal to d cos theta. And now the phase difference can be calculated in this way. The corresponding phase difference between two labeling elements should be equal to d cosine and then divided by lambda. And lambda is usually a whole wavelength. The whole wavelength should be equivalent to 2 pi. So this is what I think. And let's call this path difference, the difference in terms of phase, because of the spacing here will be equal to by this. And now Um, Another beauty of the antenna array is, as I told you, is steerable. The direction can be changed according to what? According to the phase. And instead of using the phase as a result of this spacing, you can also artificially add some more phase or less phase into the system in order to come up with a suitable value. So the total phase difference can be calculated, can be artificially engineered. You can just add more delay or less delay. And this relation is represented by alpha. And this is so-called progressive phase shift or artificial phase shift. And plus what? Plus the original one here. So the perhaps we should simplify this. 2 pi divided by lambda is k. Yeah, let's use this. So k times d beta. So k here is equivalent to 2 pi divided by lambda. So I would say where k is equal to 2 pi divided by lambda. And with this in mind, the total phase shift would be alpha plus this value. What is this value? K d cos beta. And this is the standard way of dealing with the ordinary antenna array. And with this phase difference, you can work out the direction of the beam and where the maximum is. Okay, so let's write down the important issue, right? We have the phase difference being equal to alpha plus kd cos theta. Kd cos theta, kd cosine theta is the phase difference between two labeling elements as a result of this spacing. But alpha here is artificially generated. And this is how the antenna array system works. And now, I presume you have no problem with this thing. And now, at the far end, at the receiver, at the far destination, they will receive all the electric field coming from each element of this antenna array. And the contribution of the total electric field should be calculated. And now I'm going to do it for you. The first one here will end up with a electric field. And say I naught. We don't know what I naught is. I naught can be a constant. It can be a function dependent on the direction. And let's do it. So the total electric field, total electric field received from the destination at the receiving end is from the first element. Is so-called I naught, right? Let's assume that. Right, go on. And the second one, how about the second one? The second one would be, according to the diagram here, it would be I know, and then you have to account for this delay, and this delay, according to here, is J 35. And the third one will be I know. Sorry. And this process go on and on until the end. The end minus one. And it will be I know J n minus one and then 5. And this is how the system works. And if you are going to add all of them together, the function will look like this. So I is equal to so maybe I should say the total electric field. The total electric field is going to be I naught plus I naught plus I naught. And the processes keep going until we reach the last element. The last element should be n minus 1 beta. And this is how the system works. And now we are going to simplify this expression and try to come up with a formula representing E, the value E. And what we can do is, to solve this equation, we multiply the left and right of this equation by, say, J multiply this and see what happens. Now the left side of the equation is going to be E and then times E. The right side of the equation would be the first one, it will be scaled up by this amount, exponential. The second one will be 2 alpha. And then this process just go on and on until the last one. The last one is going to be I naught and then J n. So you have two equations here. And to solve this system of equations, you just got to find the difference between 1 and 2. And 1 minus 2, and let's see what's going on. The left side of the equation is going to be E and then 1 minus this one. The right side of the equation, just be careful, right? Take a look here. This term and this term cancel off with each other. This one cancel off. And then the process going on, this one will be subtract as well. So what we end up with finally, with this term and the last term. So I know this will be the equation after a lot of simplification. And this, this equation is obviously very easy to resolve. Well, at the end, what we can get is E is the top one, yeah, we will end up with a rational expression. And one plus, sorry, I should be minus. It should be minus. Let's see, yeah, minus. And this expression can also be further simplified. So we have equation 1, equation 2 here. Yeah? And we don't use equation 2. We can just write equation 2 here. And we can, sorry, we need it. So this will be equation 3. So now the next step is to further simplify this expression. This expression is already very simple. But the problem is you have a complex function here and complex function here. And if you are asked to plot the electric field from this one here, it's difficult because you have a complex, the whole expression is complex. And that's why we need to further simplify this expression. It's not difficult. And just by looking here, all you need to do is to just do some algebraic manipulation. And if you do it carefully, what you will end up with here will be E, and then we can just extract the term. Let me see. Yeah, J, and yeah, we should extract this term here so that the term here can be written as minus J, and this one here will be J and theta. And we can continue here. The bottom of this expression is going to be J phi and divided by 2. And then J phi divided by 2. And this, you have to remember there's a minus here. So just by looking at the expression, right, if you divide the top and bottom by 2J, then you will be able to come up with a nice and clean formula. Oh, sorry, I forgot to write this. So what you end up with here is the top one you end up with, the top expression you end up with sine Yeah, because this is obviously a sine function. Uh, And you will have n, and then at the bottom, it will be sine. So the final expression is a nice and clean formula. It is it's like that. You have three parts. Perhaps we can rearrange this expression. This this expression is going to be a real number, and this one is going to be some kind of value, right? Uh, and this one here is going to be a complex number. This one is not going to affect the magnitude. The only thing that can affect the magnitude is this one here. So we have a special term for this expression, and this function here is so-called array factor. This one here is called phase factor because it only affects the phase. And finally, I know can be a complex number, it can be a constant, or any function that is dependent on the direction. So for the time being, we just ignore uh, the detail of inox. Inox is the radiation pattern coming from the individual antenna here. Now, we have already got this very important formula. And we are going to look at this. We are going to use an example to illustrate the use of this formula. Yes. So what I can do is we free up this space here, and then try to resolve an example. Now, for example, suppose you have an antenna array. The antenna array have three elements, and the spacing between two labeling elements is, say, uh, lambda divided by 2. And now the question asks, let's draw a radiation pattern. Draw the radiation pattern for this array. So what we can do is to make good use of this formula. Uh, and again, so we need to give an assumption or assume the uh, elements, each of the elements in the antenna array is isotropic. So now what we can do now is to plug in the number. Uh, so this one is going to be the array factor. Array factor is going to be, according to here, is sine n divided by this amount. And now we need to work out the phase difference. It's going to be alpha plus kd cos theta. And alpha is 0, yeah, assuming that there is no one adding any phase shift between two labeling elements. And what we will end up with here is a 2 pi over lambda, and then lambda divided by 2. And eventually, what you have here is pi cos theta. And we are going to draw the isotropic pattern. And before doing this, we are going to work out the array factor. Sine, and the top expression is going to be 3 over 2, and then this value, pi, and then the bottom expression is going to be and according to this expression, the maximum will happen when phi is 0. So what we can do is just continue. To be able to draw the radiation pattern, you need to have some information. One of the important details is the major loop. The major loop is the loop with the largest amount of radiation energy. And it happens when theta is 0. When phi is equal to 0. Or equally, right? When the expression here is equal to, when AF is equal to, sorry, when AF is maximum. When the angle here. So if this is the case, zero, the the only angle that will end up with 0 is uh, is what? Um, 90 degree plus or minus 90 degree. So based on this piece of information, we know that the radiation pattern will be maximum, and so let's say you are now drawing the polar diagram Z, and then uh, Y, uh, the let me see, or equally, right? Make it simple. Let's say this is V and this is X, right? Uh, so here will be 90 degree, and here will be and here will be and here will be minus 90 degree. Okay. So what we can do is what we know is uh, there will be a maximum at these 2 points. And we also know that based on this sin function, the maximum value will be n. So n is 3. So we expect here to be 3. And this one will be minus 3 here. So this is what we know. The second thing that we need to know is the first knows the new. So I'm going to show you. We need to find out all the nodes. Nodes happens when the array factor is equal to 0. Now, but the phase shift is not 0. And let's see what happens. And we are going to equate this function to 0. This one. And we will see what we are going to get. So based on this function, the only way that you will end up with 0 is for this value being equals to plus or minus pi over 2. And if we continue to resolve it, we have to resolve this equation separately. So, case 1, when this expression is equals to, when this angle is equals to pi over 2, and let's see what happens. Pi over 2. And if you work it out clearly, if you work it out very carefully, you will find that theta here is going to be, let me see, pi over 2. Is it correct? Pi over 2. 1/3. So bear with me for a second. Uh, Let me see. It shouldn't be pi over 2. I mix up here. It should be pi. So case 1, pass pi and see what we are going to get. And if you work out carefully, you will find theta is equal to plus or minus 48 degrees. So the zero that you will end up with here is um, 48 degrees and minus 48 degrees. And now we can continue to solve this problem. We have already worked out the case when this angle becomes plus pi, and we have not worked out minus pi, and we are going to continue here. And let's say, um, have you already included all the information? Yeah, we keep it here, and then here, maybe you need to write down, otherwise you forget it. Pi cosine theta. Yeah, okay, I'm going to continue. So in this case, case 2, minus pi, when the function becomes minus pi. And according to my calculation, if my understanding is correct, you will end up with an angle for the another, will be plus or minus 1v1. And in this case, it will be here. 1v1, it should be here. 1v1 and something like this, right? So eventually, you will end up with a radiation pattern for the main lobe. If my understanding is correct, your radiation pattern should be like this. But we haven't finished yet. After working out the node and the major lobe, you also need to find out the minor lobe. And this is what we are going to do here. But the minus group is so-called grading groups. And the grading groups normally happens when this angle become 2 pi phi divided by 2 pi. And let's do it. and we are going to work out the direction of the grading loops according to what we can get here. The angle has to be equal to uh, b divided by 2 pi. And if this is the case, then you will get anywhere with 1. And in this case, theta has to be 0 degree or 180 degree. So we have two loops here, and uh, we have this one, and we don't know the magnitude. The magnitude will most likely depends on the function here. And we do that, then yeah. By the way, so you will have another mark, so-called grading loop. The grading loop will be here, and yeah, this is what I expect. So this is the radiation pattern, and to prove it to you, I'm going uh, to use MATLAB to draw this radiation pattern. So first of all, you are now looking at the MATLAB window, and at this point, I'm going to show you. I have I have a program, and I can draw the radiation program, the radiation pattern using the program here. The program is that much. It's difficult to read at this stage, but I can just give you some hints here. The program has an interface where you can insert some of the parameters. In this case, I have shown uh, the isotropic antenna has a radiation being equal to 1, and we have 3 elements, so I put n equal to 3 here. And the spacing between two labeled n elements is 0.5. And we have shown the value of alpha is 0. Alpha is the progressive phase shift. Now I'm going to run this program. So this is what you are going to expect, and I'm going to show you. So this is the final radiation pattern based on what we can get from the MATLAB program. And this program was developed by myself. And you can see that the peak value for the major group is 3. This is exactly what we have concluded from this example. And we also have two grading groups pointing to 0 degree and also 180 degree. Horizontal. And more importantly, I just want to show you we can adjust the value of alpha. Originally, alpha is 0. Alpha is assumed to be 0. This means originally we have assumed uh, the antenna array is not going to be touched by human, and we are not going to artificially change phasor. But now if you add alpha in this case, can you see the difference? We can shift the direction of the beam. We can steer the beam away from the original position. You can also make it horizontal. In this case, it's going to be an n-wire array. I hope this is illustrative enough for you. If you have any question, please leave your questions to the comments box of the YouTube video, right? The comments box underneath the video. Thank you very much. See you next time.